All right, so here's part two, including a full example of how to find the confidence interval if you are estimating the population proportion. So two early apologies. One is the cat just woke up from a nap, so you will probably hear her in the background, and apparently my neighbor is undergoing some sort of major construction project, so there might be sawing also. But anyway, so for this example, you have that 2009 survey of 800 randomly sampled teens in the US. Teens were asked whether they have ever used their cell phone to text while driving. Of the 800 teens, 272 indicated that they text while driving. We want to obtain a 90% confidence interval for the proportion of American teens who text while driving. So two things to point out, just because when I read this the first time, I thought, wow, that number seems low. It was 2009, and there's that possibility that the teens aren't going to be super honest with you necessarily. We'll see. You never really know, but just based on this sample, let's see what we can do. So first step is to calculate your p hat, your point estimate. We have an x value, the number of observed teens who admitted to texting while driving. We have a sample size of 800. 272 divided by 800 is 0.34. You are supposed to keep 3 decimal places. In this case, it works out that that third one is a 0, so it doesn't really make a difference. We need to check if the population can be assumed to be normal using p hat as our estimate, q hat as an estimate. N times p hat times q hat gives us 179.52. We only need it to be at 10. That is way above what we need. So since that value is greater than 10 and a sample of 800 teens is definitely less than 5% of the population of all teens in the United States, so we can say that the sampling distribution for p hat is normal. Now, step 3, we have to figure out what alpha is. Since we want a 90% confidence interval, alpha is the other 10%. We want to interpret alpha as a decimal value, like a probability, instead of a percentage, so we use 0.10. And we want to find the critical value, the z-value, related to that alpha. Now, again, that means that if it's a 90% confidence interval, the 90% is in the middle. The 10% is split into the two tails. So there's one tail of 5% and the second tail of 5%. So we want to use the 5% as our alpha over 2. So in StatsMate, we would go into the normal distribution, put our probability at 0.05, and then in the A box at the top, it shows us what our z-value is, which is 1.645. Then we want to estimate the standard error of the mean, or standard deviation, using the square root of p hat times q hat over n. I mentioned this in class before, but for this particular formula, you don't have to worry about parentheses or order of operations in your calculator. You can just type the square root function, do not close any parentheses, type the value of p hat, press the multiplication sign, type the value of q hat, press the division sign, type the value of n. I only put parentheses in the formula when I typed it on this screen because it just makes it look a little nicer. They are not necessary for calculating the correct value in a calculator. So anyway, that being said, the standard deviation works out to being 0.017. The reason we need the critical value and the standard deviation is so we can calculate the margin of error. So you multiply those two answers together to get the margin of error, which is 0.028. Similarly to the last chapter, because we're working with proportions and proportions are always between 0 and 1, we keep 3 decimal places because it's more accurate, and anyway, it's just more accurate. There's no and there. Then you want to calculate the upper bound and the lower bound of your confidence interval by taking your point estimate from step 1 and adding and subtracting your margin of error that we just calculated. So the lower bound is p hat minus the margin of error, so it's 0.34 minus 0.028. That gives us a lower bound of 0.312. And the upper bound, you add the margin of error instead, gives us 0.368. Most important part is interpreting what that means. So what that means is we can say we are 90% confident that the population proportion of American teens who text while driving is between 0.312 and 0.368. You might also be asked to say something like, or to acknowledge the interpretation that means 90% of the confidence intervals that we would construct will actually contain the true population proportion of teens who text while driving, and the other 10% will not. But I'm more worried about this particular interpretation as opposed to the other one. Okay, so to do all the same work with the graphing calculator is way faster, first of all, and I'm not going to test you on using the formula. Personally, that's not really what I'm interested in at this level. I think it's more important to be able to interpret it than to plug and chug through the formulas. So the graphing calculator already has something set up for you. If you press the stat button and go over to the tests menu and scroll down for a little bit, you'll find one that's labeled A, because they ran out of numbers, and that's the one proportion Z interval. It's a Z interval because your critical value is a Z value, and it's one proportion because we have one sample and we're calculating a proportion based on that one sample. It prompts you to enter the value of X, that's the number of observed successes or the number of individuals with that characteristic you're looking for. It asks you to enter the value of N, or your sample size, and it asks you to enter the C level, which is the confidence level, and you do need to type it in decimal form, not as a full percentage. Highlight where it says calculate and press the enter key. The graphing calculator will show you a screen with parentheses at the top and two decimal values separated by a comma. The first value is the lower bound of the interval. The second value is the upper bound of the interval. It will also show you the calculated value of p hat underneath in case you needed it for some part of your calculation or you didn't do it ahead of time. Okay, and then there's determining a required sample size. I don't focus as much on this, but there are some practice problems related to it. So this would be if you were the researcher and you wanted to make sure you had enough individuals in your sample to be able to calculate a confidence interval. So if you have information to calculate p hat, then the sample size that's required for the confidence interval can be calculated using this formula. Okay, you take p hat times q hat times the critical value divided by margin of error squared. In this formula, parentheses are important. If you're going to do this in multiple steps in a calculator, you need to take the critical value divided by margin of error first. Like, do that number divided by other number, hit enter. And then you can press the x squared key. It'll say answer squared on your screen. Press enter. And then you can multiply by p hat times q hat. That you can all have in as one step. But just make sure you either have those parentheses or you break up the steps for how you enter that in a calculator. If you don't know what p hat is, if you don't have any sample data, then the sample size that you need, you can assume that p hat times q hat has a maximum value of 0.25, because the largest possible value for p hat and q hat, like for them to equal each other, that's when you have the largest possible number for both. P hat times q hat, if they're both 0.5, if they have equal probability, 0.5 times 0.5 is 0.25. Anyway, so you just replace the p hat times q hat with that maximum possible value of 0.25 to make sure you have enough individuals. You always want to round up, so like if I get that the answer is 18.02, I still need to round up to 19 individuals, because if I only use 18, then I decided that 0.02 wasn't really important. I'm going to end up with an n times p times q that's less than 10, so I wouldn't be able to make a confidence interval. Okay, so for example, an economist wants to know if the proportion of the US population who commutes to work via carpooling is increasing. What size sample should be obtained if the economist wants an estimate within 2 percentage points of the true proportion with 95% confidence if the economist uses the 2006 estimate of 10.7% obtained from the American Community Survey. So what's annoying about this is trying to figure out what they're actually telling you. So I'll break it down one point at a time. The first thing that they tell you up here is that the economist wants an estimate within 2 percentage points. When they say within, that's giving you a clue that they're about to tell you the margin of error. So this is telling us that the margin of error is 2 percentage points. 2 percentage points is the same as a decimal value of 0.02, because 2% is 0.02 when in decimal form. The 95% confidence level is telling you what value you need to use for alpha, which is 0.05. And it's also letting you know, okay, you need to find the critical value for alpha over 2, which is 0.025, and that would give you a z value of 1.96, like we calculated earlier. And then it says they're using the 2006 estimate of 10.7% who carpool. That 10.7% is actually your p-hat. It's a previous estimate of the proportion of the Americans who commute to work by carpooling. So that would give us a p-hat of 0.107. So there's all of that summarized again. Now I just need to plug what I know into the formula that I have. If p-hat is 0.107, that means q-hat has to be the 0.893 it takes to add up to 1. Okay, I put in my critical value 1.96, my margin of error 0.02, and when you enter all of that correctly into the calculator, you get an N of 917.67. And remember, you have to round that up to 918. So the economist should use a random sample of at least 918 Americans in the study. If they want to know if the proportion of the U.S. population who commutes is increasing and they do not use any prior estimates. So this whole setup right here is exactly the same as the previous slide. It's just saying here that they do not use any prior estimates. Since we are not using any prior estimates, we don't know p-hat, so we have to use that formula that has the 0.25 in front. Our critical value is still the same because it's still 95%. Our margin of error is still the same because it's still saying within 2 percentage points. This time I got a much larger sample size required. It's 2401. So you need a random sample of at least that many working Americans in the study. And any time that you do this, you're going to need a larger sample when you don't have a prior estimate for P, because you're assuming worst case scenario, or you're assuming that there's an equal chance of success and failure. So that was actually it. I didn't realize I was on the last slide. The next video will be about confidence intervals and required sample sizes if you are estimating a population mean instead of population proportion.